Hello and welcome to this lecture on fundamentals of electric drives. In the last lecture, we were discussing about the commutation process of a converter fed synchronous motor drive, which is load commutated, and we saw that the load back EMF are used for commutation of SCRs of the converter. Let us assume that let us say we had the conduction of let us say T6, these two SCRs were in conduction. So, when these two SCRs were in conduction, what is the DC voltage, the DC link voltage here? Now, this SCR is conduction, this is on, this SCR is also conducting. So, we have the current flowing like this. So, this point is connected to this point here. So, this is how the current is flowing. Similarly, the current is flowing in this case like this. The current is coming from the DC link all the way. So, what is VDL? So, VDL is with this positive and this negative. So, what is VDL? VDL is this point is basically coming from C through the commutation inductor. So, we can say that VDL is almost equal to V C and then this point is B. So, V C B. We can ignore the drop across the inductor for the time being. So, VDL is V C B. And now, what we do? We trigger the SCR which is T1. When we trigger the SCR which is T1, and this was basically for the previous case that T5 and T6 were conducting. Now, what we do here? We trigger SCR T1 when this SCR is triggered. So, this has to be forward biased. So, it means VAC has to be positive. So, VAC has to be positive. This is the point A, this is also B and this is C, if we ignore the drop here approximately. So, VAC has to be positive. So, the SCR T1 is forward biased and T5 will be gradually reverse biased. So, it was carrying this current through this, and this current was coming all the way from the synchronous machine, and this current was flowing like this. So, the current was coming from the synchronous machine. So, what we are trying to do? We are trying to turn off T5 and turn on T1. So, the current was flowing through an inductor. So, the inductor current cannot be turned off immediately. So, this current will take some time to die down, and this is a negative current because this is opposite to the convention of IC. So, when we trigger T1, this will also pass a current. So, this current will also try to flow here, and this current will come from phase A. This current will come from phase A. So, the current will come from phase A, and the contribution of ID is here, and the same ID is flowing in this case, will be because of Ti5. So, we can say that this is IT5 and IT1, which is ultimately are the current of the phases of the synchronous motor. Now, we are trying to change it to this situation. VDL should be equal to VAB. So, this is fully possible when T1 and T6 are conducting, T1 and T6 are conducting. For a small time, we have the conduction of T5, T6, T1. So, this time for which there is a transition, this time is called the overlap time. This is called the overlap time. So, in fact, when we change from T5 T6 to T1 T6, we will have the time for which both T5 and T1 is conducting. This is called the overlap time. Now, we will try to analyze it further here. Now, in this case, if we see the equivalent circuit, we can draw the equivalent circuit here. So, we have T6 was conducting. So, the phase B was conducting here. So, this is phase B, and then T5 was earlier conducting. So, this was connected to phase C. So, this is our motor. So, we have the motor back EMFs here, individual back EMFs. This is B, this is A, and this is C. So, this is connected to phase C, and now what we do here, we trigger thyristor T1. This is T5 and this is T1. So, when we trigger T1, this is connected to phase A. This is phase A here. So, these are the commutating inductors, and the process is like this. So, this is our DC link voltage, which is VDL with this positive and this negative, and this current is ID, and ID is flowing back here. So, we have to understand this particular commutation process. So, earlier the current was flowing through this. So, these are the individual current IA, IB and IC. So, this current is IC. So, we can say that ID, here we can apply the Kirchhoff's current law. If we apply the Kirchhoff's current law, we can say that ID is equal to minus IA plus IC. So, this current is IC and this current is IA. Actually, the current will be flowing in the opposite direction, but however, if you maintain this current direction. So, ID plus IA plus IC equal to 0 or ID equal to minus of IA plus IC. So, we can differentiate this d by dt of ID is equal to minus d by dt of IA plus IC. So, ID is constant, the DC link current is almost constant. So, therefore, d by dt of ID is equal to 0, that is equal to minus dIA by dt minus dIC by dt. So, we will get from this equation that dIA by dt is equal to minus dIC by dt. So, this is the derivation that we have. So, the rate of change of these currents are equal and opposite. So, here if we plot the phase current, let us say we plot here IA. So, at this instant we are triggering T1. So, T1 is triggered here T1. So, what will be this current? The current IA will gradually rise from 0 and this will become negative finally, and this is the overlap time. This is mu. So, this will continue to flow here. So, till this point, because this is VAB and then we have VAC, and then from this point this will be taken over by VBC. So, the current IA will have a negative value like this, and here again we have the commutation overlap. This is the angle mu again. So, the nature of the current IA will be quasi rectangular or quasi square wave, but this will be this is VCA. So, here the current will have a decreasing value. So, this value is ID and this is also ID. So, the nature of IA will be of this sort. And what about the nature of IC? At this instant, if we draw IC at the commutation instant here, IC was initially negative. It was carrying this current C phase current, and when T1 is triggered, IC will gradually decrease like this, and when IA reaches negative maximum, IC will reach 0. And the slope of this is a decreasing slope and this is an increasing slope are equal and opposite. So, this is the value of IC will be a decreasing current like this. So, this is the commutation interval, that is mu. So, this mu is also shown here, this is the commutation interval, that is mu. Now, if you start from this, we see that VAC is becoming positive here. So, this is the instant of the triggering of this is the beginning of the reference from which we can trigger the SCR T1. So, this is the triggering angle, and so the triggering can continue from this point till this point, and whatever is remaining here is called beta. Beta is the commutation lead angle. So, we say that alpha L is the triggering angle and beta L is the commutation lead angle, which is 180 degree minus alpha L. It means when we are triggering an SCR in an inverter thyristor, there is some angle which is available for the successful commutation. That angle is beta L, and again we have an overlap angle. So, this beta L is 180 degree minus alpha L, this is called the commutation lead angle. So, this is 180 degree, this is 180 degree here from this point to this point. So, whatever is remaining in this case 180 degree minus alpha L is beta L. So, the beta L here, this is 180 degree completely, beta L is the commutation lead angle. Now, we will be will introduce two angle which is called the margin angle, gamma. So, gamma is called the margin angle, gamma is called the margin angle. So, what is this margin angle? Margin angle is equal to 180 degree minus alpha L plus mu. So, whatever is remaining from 180 degree minus alpha L plus mu is called the margin angle. So, this margin angle is the angle which ensures successful turn off of the SCR. We can see here that this voltage, this voltage is giving the forward bias to T1 here VAC, VAC is giving the forward bias to the SCR T1, is also reverse biasing the SCR T5, and for the time from this instant to this instant, the starting instant to this instant, SCR T1 is forward biased. So, it means whatever angle is remaining, that angle is called the margin angle, because during the overlap period mu, both the SCRs are conducting. So, this is the time available or the angle available for successful commutation of inverter SCR, and this should be higher than gamma should be in fact higher than T into omega into TQ, where TQ is the turn of time of an SCR. Let us just come back to our analysis of commutation. So, we saw that this is our equation, that the current has to be the rate of change of current is equal and opposite. Now, if we go back here, we have a loop in this case, and in this loop, which is the loop here, we have a loop which is like this. It is a closed loop. So, we can apply the Kirchhoff's voltage law. So, if we apply the Kirchhoff's voltage law in this closed loop, what we get here is this is VAC, and we have the drop across this inductor which is LC dIA by dt. We have drop across this inductor which is LC dIC by dt. So, if we apply the Kirchhoff's voltage law in this loop, so applying KVL, in the commutation loop, we can write here that VAC plus LC dIA by dt minus LC dIC by dt is equal to 0. So, this is LC dIA by dt. So, if you proceed from this point, so we will see that there is an increase of the potential, and then if we go from this point, so we see there is a decrease of the potential. So, this is the equation that we have, and we can apply our equation 1, let us say this is our equation 2. So, we can substitute for, let us say, dIA by dt and simplify. So, we will see that 2 LC dIA by dt is equal to minus VAC, or dIA by dt is 1 by 2 omega LC into VAC into. So, this is the equation that we have. Now, if we see this current IA, the current IA builds up to the value that is ID. So, this is the time for this, and VAC is a sine wave starting from this point. So, we can find out this by means of an integration. So, we see that ID, or in fact minus ID, is equal to minus 1 by 2 omega of VAC into d omega t. Limit here will be from, this is our VAC. So, we are starting from alpha here, VAC is positive, that is a sine wave, alpha to alpha L to alpha L plus mu. So, this is our integration limit, and what is VAC? VAC is the line voltage. So, minus 1 by 2 omega LC. So, this is V line, this is the RMS value. So, if you want to get the peak value, we can multiply here by root 2 into sin omega t d omega. Integrate this from alpha L to alpha L plus mu. So, that integration will give us the following. So, root 2 V line to line by 2 omega L. We have sin omega t, the integration of that is minus cos omega t. So, we get here cos alpha L minus cos plus mu. So, I can remove this minus sign from both the sides, get this equation I d to line. So, root 2 V line to line by 2 omega L C. So, we get here cos alpha L minus cos L plus mu. So, this is the equation. In fact, this is a very equation which gives us a value of the with a given value of alpha L. So, regarding angle, if we know the current I d, if we know the V L L, we can get the value of mu. So, in fact, from this mu can be evaluated. Mu can be from, let us say we call this to be from 3 for given alpha L I d for a given alpha L d and I d. If we know alpha L, we can find out what is the value of. Now, the commutation process down the current that is a delay and the delay phase lag. Now, we have a converter AC to DC, another converter or an inverter AC to synchronous machine. Let us closed loop block diagram where the synchronous machine is controlled. So, we have block diagram loop speed control. So, we have two converters. We have a source side converter, we have a load side converter which is a CS, and then we have motor. This feeds the synchronous motor. Converter C voltage have the and the DC link, in this case 3 phase or AC supply. So, this is converted to DC. So, we have DS and then VDL water the load side. So, we can have sensor. So, this is the terminal voltage sensor voltage. So, this senses the terminal voltage of the synchronous motor. So, we have to synchronize the motor with the frequency. So, what we get here the frequency of the terminal voltage and the of the rotor. We may not have a position sensor here, but the position of the motor can be the terminal voltage. So, this is from this what we do here, we give a reference speed, in this case omega, and we compare the reference speed with the actual speed which we obtain from this terminal voltage sensor. Have a differential speed, then we have a speed sensor or speed controller, which is a P. So, this is the speed error, and the output of the goes to a. So, we have a current limiter, the value of the output current to a safe value, and this output of the is ID star reference. The ID reference is compared with the actual value of the ID. So, we have a sense which senses the actual value of ID. So, we have a current sensor, the actual value of ID is sensed here, and then we current controller, triggering circuit of the current error, the current controller and the triggers gives, that is alpha S. The load side converter controlled by, and then we have a firing. So, what we do here, we give the alpha L, the load side firing angle. So, and also the frequency basically is given here. So, this basically gives delay block. Phase delay block gets the frequency from the voltage sensor. Break the sign of this error and the phase is changed by 180 degree. So, this is the closed loop speed control synchronous. Now, we see that here we have a closed loop feedback. Since feedback, this drive is a self controlled drive, instability not go out of state. So, these are the drives which are used for high power applications. So, with this we stop here for today's lecture. We will continue our discussion in the next lecture.